Greetings, Saintsmen. I have for you section 1.5, Measuring Angles. I want us to consider one of the figures that we discussed early in this textbook so far, early in this course so far, which is the ray. When we have two rays that share the same endpoint, this guy right here, this point, what we form geometrically has a name. The name of this is an angle. Those two rays are considered to be the sides of the angle, and that shared common endpoint is what's referred to as the vertex. Now, of course, we can assign this a name. So in order to do this, the proper notation, I'm going to add a couple of points on each of these rays. So I'm going to have A, I'm going to name the vertex B, I'm going to have C, and additionally, I'm going to have a 1 inside of this angle. There are three ways we can consider this. Whenever we name an angle, we're going to do it using 3 points. We're going to have it A, B, C, or the other way that we could name the same angle is through C, B, A. Now notice what these two things have in common. They both have B as the point that's listed in the middle, and that's because the vertex is always going to be that middle listed point in the 3 points when we are discussing an angle. So note that ABC and CBA are the same exact thing because the vertex is listed in the middle. If I were listing a different angle, I wouldn't use, for example, angle ACB. That wouldn't be the same thing because here C would be the vertex, and obviously that is not the vertex right there, right? Vertex is that shared common endpoint. There's one other way which mathematicians have decided together and have come to a consensus that we can also number angles. So mathematicians, we like shortcuts. So for in this example, we're going to go with angle 1. It's faster than writing ABC or CBA. Further, let's discuss the notions of what's interior or exterior to an angle. So taking a look at this angle that we have right here, these two rays, they share a common endpoint. I would call this space shaded in blue right here the interior. And of course, all the space outside here is what we would refer to as the exterior. So you're commonly going to hear in this course the notion of interior and exterior to an angle be discussed. And now we know what we're talking about. There are 3 classifications of angles that we are going to discuss. So I'd like you to please copy down these 3 angles that I'm constructing here. The first angle is what's referred to as an acute angle. Acute angles have an angle measurement that is less than 90 degrees. One of the ways that people commonly remember this is that acute angles are the skinny ones, or the tiny angles, right? And tiny things are acute. The next angle is what's referred to as an obtuse angle, which has an angle measurement that is greater than 90 degrees. Again, a way that we can remember this is that, like, the word obese means fat, obtuse is the fat angle. So it's a similar sort of root that we have there. Next, we have this last angle, but it is very important that we don't make the assumption that this is a right angle. Here's why. It isn't noted that this is actually a right angle. There needs to be the proper notation. You cannot make any assumption about the diagram until it's actually done. So, in order for us to say this is a right angle, we are required to have a little box interior to this angle. And now this is a right angle. Which, of course, I hope through prior knowledge you know, is known as has a measure of exactly 90 degrees. Without that box, we cannot make that assumption. We have another postulate to discuss today, and this is what's known as the segment addition postulate. The segment addition postulate is where we have these three angles for the record. Now, I think some of you guys initially might see, oh, there's two angles. There's one and there's two. But also note, there is a third angle. It's that one that would be constructed through really the sum of the other two. Now, I'm going to give you guys a more accurate definition. So let's go ahead and put in, mark the common endpoint, put some other points on here. We have A, we have B, we have C, and we have D. And in our angle addition postulate, what we need to note is that if the point C is interior to angle ABD, for the record, we can do this. We did this earlier on, right there. That means angle. The little symbol right there. So rather than writing out the word angle every time, it's acceptable just to use that symbol instead. So if C is interior to ABD, as long as it's inside of that angle, creates an interior ray. So what that means is then that we have angle ABC and CBD, and that's equal to angle ABD. Or in other words, if I were to mark ABC as 1 and CBD as 2, if I have angle 1 plus angle 2, the summation of those two things is going to give me angle ABD. The two together with that common shared side, BC, will create that overall angle. Now, I'm going to add one more thing here. Separately, if I were to put these arc marks, similarly to where we used line segments and we used tick marks, we were denoting congruence. So if I were to show that those two angles, angle 1 and 2, have those same number of arc marks, I can make the conclusion that angle 1 and angle 2 are congruent. If that's the case, with those two angles being adjacent, it means that ray BC is the angle bisector. Now, remember when we had segment bisectors, it meant that we created two equal parts. That's exactly what we have here with an angle bisector. We have this bisect, right? Like bicycle has two wheels. Bisect means two sections, right? So we have two equal parts or two equal angles that are created from that. Now, let's attempt some problems using this information. All right, so I have a triangle here. I have triangle D, E, F. And in triangle DEF, I'm going to mark some of the angles. So the question is, if we have angle EDF and it is equal to 40 degrees, then how much is angle EFD going to be? Remember what we've learned. Think about, in EDF, what is going to be our vertex? Well, it's D. So we go E, D, F. D is our vertex. Similarly, with EFD, F is our middle letter, so therefore that is our vertex right here. So we go E, F, then D. Notice that they have the same number of arc marks. So what does that mean? Well, in conclusion, it means that those are congruent. They will have the same measure, so EFD will also be 40 degrees. Next. Let's draw another set of angles, and I have A, I have V, I have B, and I have C. So you know what? Before we do that, let's actually erase that, because I think sometimes it's challenging for us if we don't have the diagram. Let's construct our diagram after we're done, okay? So if we have angle ABC equal to 58 degrees, I have a little shortcut for my degree symbol on here, so I have to draw it. And VB, which is a ray, is the angle bisector. Then, what is the measurement of angle AVB? So think about what we have here, right? We have, it's saying AVC, which is an angle, so let's create angle AVC. A, we know that V is the middle letter, so therefore it's our vertex. And C. And then we have VB as an angle bisector. So let's go ahead and cut that guy in half. V, it's ray VB, so we know V is that endpoint, and we know that B is going to be on that ray. So there we go. What that means then, if it's the angle bisector, we should know that this angle and this angle are both congruent. Now, each time I've drawn this with 2 arc marks, you can actually also do this with just 1. Or you can do it with 3, or you can do it with 4, right? It's just like the number of tick marks that we use. But what it wouldn't mean is that I do 1 arc mark here in, for BVC and 2 for AVB, right? That's silly. It's going to be the same number, means it's the same angle measure. Okay. So if that's the case, then AVB, this angle that's congruent to BVC, well, it means that, again, this was cut into 2 congruent parts. So that means that angle AVB is going to be whatever 58 divided by 2 is, which is 29 degrees. All right. And our last example now. This one I'm going to draw ahead of time for you. I think sometimes it's difficult for us to interpret the words and create our own diagram, which is why I did that first last time. But here, we're actually given a diagram. In our angles, we have P, we have Q, we have S, we have R. We have no indication as to whether or not QS is an angle bisector. Moreover, if PQS and SQ are congruent. What we are given here is that PQS is equal to 7x minus 5 degrees, and SQR is equal to 9x plus 11 degrees. And that the measure of angle PQR is equal to 102 degrees. So what we are charged with finding, oh, this is a new thing too, we just saw. Don't overthink this. That M, it just means the measure of the angle, okay? That's not a variable. So this is another form of notation that's used. It's not that big of a deal. So we're gonna find the measure of angle PQS and measure of angle SQR. One of the things that's, when that's used, it means that we don't need to put the degree symbol, okay? So, when we complete these problems, similarly, when we had to provide a segment addition statement, we need to also provide an angle addition statement here. So we'll need to find PQS and SQR. We know that PQR is 102, but moreover, look at your diagram. Think about your angle addition postulate. We know that if we take the sum of PQS and SQR, that's going to create angle PQR. Or conversely, that PQR is the sum of PQS and SQR. And now, let's substitute. We actually have values that we can substitute for each of these angles. For example, PQS is really equal to 7x minus 5. SQR is really equal to 9x plus 11, and PQR was given to us that it's equal to 102. This is now a very straightforward algebra problem for you. So let's go ahead and tackle it. We're going to combine our terms. 7x plus 9x is 16x. Negative 5 plus 11 is 6. We'll bring down 102. And now we have a two-step equation, right? Let's go ahead and subtract 6 from both sides. So we're left with, on the left side, 16x. 102 minus 6 is 96. And then to get the x by itself, we're going to divide both sides by 16. The 16s on the left side are going to factor out, and x is equal to the result of 96 divided by 16, which if you put it in your calculator, you're going to find that is equal to 6. Now, students, here's the issue. Some of you will stop this problem and be so proud of all that algebra that you did, that you set up the problem properly, and you're going to just stop right here and you're not going to get credit for the problem. You're going to get a deduction for your solution. The reason why is because we weren't asked what x was. We were asked what PQS and SQR are. So let's solve those. We know that PQS in the problem was given to us as 7x minus 5, so we're going to actually plug x back in as 6, or 6 back in as x. So 7 times 6 minus 5, which is equal to 37. So PQS is 37 degrees. Also, we need SQR, which was given to us as 9x plus 11. So we're going to take 9 times, we know x is 6 plus 11. 9 times 6 is 54 plus 11 is 65. So that one is 65 degrees. Now we've officially solved the problem. As a quick check, think about this. The two values, PQS and SQR, when added together, will equal PQR, which was 102. So go ahead and check on your own. What's 37 plus 65? All right, good luck, Saintsmen. If you have any questions, feel free to reach out to me via email. And of course, it's now time for you to tackle section 1.5.